So let us then turn to the statistics of bosons. Here the considerations are similar as above, only that the microscopic occupations of the individual states can now be any non-negative integer. What we then end up with is the expression given here, which is known as Bose-Einstein statistics. Note that as a mathematical expression, this looks very similar to the Fermi-Dirac distribution, only with a different sign in front of the 1 in the denominator. And it is exactly this difference that now allows these averages to exceed 1, reflecting situations where more than one boson occupies a given state on average. Well, for large temperatures, the occupations once more become very small, and indeed this extra factor in the denominator can then again be neglected. So also here we then approach the classical expressions of a non-degenerate system, which for a gas would lead to the Maxwell-Boltzmann distribution. The key difference is therefore the behavior at low temperatures, and in particular for energies close to the chemical potential. We see that the Bose-Einstein distribution actually diverges when the energy approaches the chemical potential. As a consequence, in thermodynamically stable bosonic systems, the chemical potential always lies below the ground state energy. And the key question is then, how close to the ground state energy does the chemical potential lie? As it happens, when we decrease the temperature, the chemical potential tends to move closer to the ground state energy. And when we evaluate the occupation of this ground state, it can happen that below a certain temperature, this becomes macroscopically large. When this occurs, a large number of particles in the system, those in the ground state, behave collectively to display all the same quantum mechanical properties, including their possibility to show wave-like interference effects. This signifies a phased transition in which quantum effects become detectable on a macroscopic level. If this happens in a gas, we call this a Bose-Einstein condensate. But similar physics is also at play in superfluidity, as in helium-4, the stable bosonic isotope of helium. But also systems made out of fermions can show a similar behavior if the fermions pair into composite particles of bosonic character. For instance, into so-called Cooper pairs, for which the interactions are mediated by quantized vibrational modes, so-called phonons. This leads, for example, to superfluidity in helium-3, the stable fermionic isotope of helium. And significantly, this also leads to superconductivity, at least in so-called conventional superconductors. Okay, to conclude this chapter, let us look at one application of Bose-Einstein statistics where we can work out everything completely. And this brings us back to the origins of quantum mechanics, namely black body radiation. So the problem studied by Max Planck in 1900. This concerns the radiation emitted by objects of a given temperature T. To quantify this, take a unit element on the surface of the body and consider how much radiation this emits into a unit solid angle. By how much radiation, we mean the radiated energy that passes through the surface in a unit of time. And finally, we would like to resolve this spectrally, so by angular frequency. This gives us the so-called spectral radiance, which I denote here as I. And the key dependence that we are interested in is how this changes with temperature and angular frequency. Now, as many flux-like properties, this can be split up into a density and a velocity. Perhaps you recall how this even applied to the probability flux in quantum mechanics. Here we therefore have the spectrally resolved energy density of the electromagnetic field, U, multiplied by the speed of light, c. Just as a reminder, besides this additional division by 4 pi, which comes from the unit solid angle, we already encountered this relation before when we discussed radiative transitions with the help of Fermi's golden rule and introduced the Einstein coefficients. And indeed, it is again Einstein who provides us with the key insight into the subsequent step, which Planck carried out in a more heuristic fashion. Namely, being able to refer back to the concept of a photon, we can now express the energy density as a product of the energy per photon, so h bar omega, times the spectrally resolved density of available states, so the local density of states nu, and the average occupation of these states. Then we insert here the corresponding local density of states for photons, where we include the twofold degeneracy due to the polarization degree of freedom and the Bose-Einstein distribution for the average occupations. In the latter, we set the chemical potential to 0. This is because photons can be freely created and destroyed. And now when we insert all of this into the expression for the spectral radiance, we obtain the final result as given here. This is Planck's law expressed in terms of angular frequencies. We obtain it in its original form when we re-express it in terms of the ordinary frequency f. We can look at two limits, namely that of very small and very large frequencies. For very small frequencies, we can approximate the result by the Rayleigh-Jeans law, which can be independently motivated from classical electromagnetism. At very large frequencies, we obtain an approximation as before applied to a dilute, non-degenerate gas, so a classical picture but based on particles instead of waves. This is known as the Wien approximation. Planck's law beautifully reconciles and unifies these wave-like and particle-like descriptions, just as quantum theory did as soon as it was fully established. Note that besides the variables, Planck's result only involves fundamental constants, c, the speed of light, and h, hence Planck's constant. And so this central thermodynamic phenomenon was indeed an ideal starting point to develop this theory. But now that we have seen this theory develop completely, we can also appreciate how rich this particular phenomenon really is. When we trace back the appearance of Planck's constant, then it really comes from the quantization of the electromagnetic energy in discrete units of h bar omega, or h times the ordinary frequency f. We also needed to count the corresponding states consistently using quantum mechanics, and finally we needed to take the bosonic nature of the photons into account. So this involves a wide range of the topics that we covered, and is indeed a good place to draw a line under the content in this course.